What I'd like to do in this short video is to show you how we fire up Crimestat and analyze data using it. I'm going to start with the data in the file book, which is page 131 of Geographic Information Analysis. So let's start by looking at those data. So simply fire up Notepad and observe that the data are in two columns, that there's no header, and that in fact on both X, which is the first column, and Y, which is the second column, the coordinates range from 0 to 100. So those are our data. Our program, Crimestat, we've got in this case in the same directory, and I simply double click on that to fire up the application. We start with this screen that tells us something about it, click into it, and what we get is the main control screen for CRIMESTATIII. You can see in fact that what we've got is a data setup screen, that's where we arrive, a spatial description screen, a spatial modeling screen, a crime travel demand screen, and some various options. And within each one of those there's an appropriate set of tabs that relate to functions that we might wish to perform within it. What we've got to do first of all is to set book as our primary file. So what we do is click on select files, and because book is an ASCII file, we need to first of all set the type to ASCII, and let's browse to find the data. I've got them in the same directory. You might have them somewhere else, but you can see I've got all three files here, and the one that we want is book, so we click on that and open it. Before leaving this section, though, it's important to note that we need to make sure that the separator is a space, that there is no header row, and that we have two columns. So in essence, that's a description of our data. So we can OK that and proceed back at the data setup screen. What we next need to do is to define where the X and Y coordinates are, X and Y in these two rows here. So X we know are in column 1 of our data, and Y we know to be in column 2. So we set those. Before leaving this screen, we need also to define the type of coordinate system, whether it be spherical in latitude, longitude, or whether it be projected as a Euclidean XY data space. In our case, they're projected, so we tick that box. The data units in our case are arbitrary. They could be feet, they could be meters, they could be centimeters, whatever, but let's set them as meters in that case, in this case. So that's set up our screen. Our data. We don't need to do anything more at this juncture. We could, if we wanted to, define a reference file, and something I'm going to do is we can define the area of interest. Now, why that's important is because we might wish to have a different area from the bounding rectangle of the data used in calculations or estimates of the intensity of the process. Well, we know in fact that our area is 100 by 100, so we've got 10,000 square meters in which our data are placed. So let's set that at 10,000. The type of distance measurement we know to be direct. It doesn't use a network distance or a so-called Manhattan distance. Don't worry over much about those. Let's now then go to spatial description and ask for the computation of the mean center and standard distance. All we do to that is click on distance analysis, click on mean center, and simply say compute. And as you can see, what's returned is a description of the data together with the minimum, maximum, and mean XY coordinates. So in the final row there, what we've got is what we're after, the coordinates of the mean center of our data. We can dismiss that file by simply closing it and go perhaps to a distance analysis, where we might wish to calculate the Clark and Evans nearest neighbor statistic, which we simply do by clicking on nearest neighbor analysis. We want just first order neighbors to be considered. We don't want a border correction, so we say compute that please. What we get is, notice now, another tab labeled NNA, which contains the results of the nearest neighbor analysis. And in this case, you can see that the mean distance to nearest neighbor is 21.61 meters in our coordinates. That I think is consistent with what we've got in the book. We've got various other measures based on it. And based on the bounding rectangle, that gives us a Clark-Evans index of 1.7, which indicates, in fact, data that are highly dispersed, much more dispersed than random. And you can see that from the z-score, z-score, and the probability associated with it. If we use our user input area of 10,000 square meters, then that cuts things down a bit. It's less dispersed in that frame. It brings it down to 1.49 or so. Again, highly statistically significant. And that's it. That's all that we need to do if we're computing nearest neighbor analyses.